Welcome back everyone. In this lecture we will see the character theory. So, first of all we want to define what are all the characters and where we are working in. So, let us actually consider these highest weight modules. Okay. So, let us actually recall what we have proved so far. So, if we start with for example Verma modules. So, if m of lambda, if this is Verma module, so then the weights of the m of lambda, so this is actually exactly equal to lambda minus n1 alpha 1 plus etcetera plus nk alpha k. So, let us write this alpha 1 etcetera alpha k to be the positive roots. So, maybe I will use a different notation. So, let us write it as beta. So, beta 1 up to beta n. So, these are the positive roots. So, where this n1 etcetera n they are all non-negative integers. So, this is something actually follows from PBW theorem. So, we will make this precise. But so for the motivation, so it is enough to see that the weights of m of lambda is actually contained in this set. So, this is just a cone that is actually bounded above by lambda. So, this is indeed lambda minus q plus. So, recall what is q plus. So, q plus is nothing but the span of z plus span of the simple roots alpha I from 1 to n. Okay. So, now similarly, like if we actually take the corresponding irreducible module, which is denoted by V of lambda, irreducible quotient of m of lambda. Again the weights of V of lambda is contained in this lambda minus q plus. Okay. So, now because of this, if we define the character to be the following thing, then we have to actually consider those weights that are supported on cones like this. Okay. Let us call them S of lambda. So, let me first define the character and then I will actually tell you where we are working in. Okay. So, we have to actually define the character ring. So, in which we do all the computations of the characters. So, first of all the character makes sense for any weight module whose weight spaces are finite dimensional. There is no issue with that. So, we can define the character in that generality. So, let us actually consider this more general version. So, the weight modules, and of course, this is all H weight modules. So, what are they? So, by definition, so they are actually just can be written as direct sum of weight spaces. So, V is a weight module, then V can be written as direct sum of V mu, where mu comes from H star. So, recall V mu by definition this is the weight space, those vector V in V such that there is this simultaneous diagnosable action. So, the H V is given by mu of H V for all H in H. Okay. So, if we have this weight space decomposition, then we call this is a H weight module. So, this is weight space decomposition. To talk about characters, we also demand the dimension of V mu to be finite for all mu in H star. Okay. So, these are the two properties that should be satisfied. So, V is said to be H weight module if V satisfies the following conditions. First one is V is being just a direct sum of weight spaces, and second thing is we demand that the dimension of V mu is finite for all mu in H star. The modules so far that we have considered, all of them satisfy this property. For example, irreducible modules, the highest weight representations, any highest weight representation satisfy this. In particularly Verma module and irreducible finite dimensional modules satisfy these conditions. So, now given this highest weight module, one can define the character of this V. So, if you think about it, we want to actually record all the data that is involved in the weight space decomposition. There are two sets of data that are actually involved. One is the weights that are there of V. Okay. So, the weights of V by definition, recall that this is those mu in H star such that mu being non-zero. So, now given mu, which is a weight, there is a weight multiplicity which is the dimension of V mu. So, given mu inside weight mu, we have this multiplicity of this mu. Sometime it is written as multiplicity of V of mu, which is defined to be the dimension of V mu. Okay. So, we want to record these weights and weight multiplicities all together. So, then what we can do, we can actually simply define this function from H star to Z. Okay. So, this is one way of actually thinking about the character. So, we can just simply define it to be a function from H star to Z. Actually, it goes to Z plus because the dimensions are all non-negative integers. So, given this mu, you just send it to the multiplicity of this mu, V mu, which is nothing but the dimension of V mu. So, this function character of V is called character of V. Okay. This character of V is called character of capital V. So, this is how one can define the character for any given highest weight module. Of course, this way of actually thinking is not very helpful. So, we want to do many manipulation, we want to do algebra with this character. So, we want to add, we want to multiply and so on. So, we have to actually understand where that multiplication, addition and so on happens. Okay. So, that is why we need to define what is called character ring. So, now recall that. So, with this definition, the character of m of lambda satisfies the following property. So, if I look at what is called the support of character of m of lambda, which is those mu inside H star such that character of m of lambda of mu is non-zero. In other words, this is nothing but the dimension of m of lambda mu. So, those multiplicities which are non-zero. So, then we see that this is indeed contained in S of lambda, which is by definition lambda minus q plus. Okay. So, given this one particular character of Verma module that is indeed contained in one cone that is bounded above by lambda, but we will see that we will be only interested in finite dimensional irreducible representations or finite dimensional representations. So, in particularly we can talk about this Jordan holder and so on, but we already proved that the category of finite dimensional representations, they are indeed completely reducible category. So, in particularly any finite dimensional representation can be written as direct sum of irreducible representations. So, that actually tells if at all you have actually character for finite dimensional representation, then we have the following property. So, let us start with V, finite dimensional representation of G, G being SLN plus 1. Then the character of V, if I take the support of this. So, support again for any character is defined to be support of, actually more generally for any function is defined to be. So, let us say function is from H star to Z plus. So, given function f, support of f is defined to be those mu in H star such that f of mu being non-zero. Okay. So, then the support of character of V for any finite dimensional representation modulo this complete reducibility, you can see that this is indeed contained in union of finitely many cones I ranging from some 1 to L. Okay. So, that means this is union of S of lambda I ranging from 1 to L. So, this actually suggests that indeed if we are interested in defining this character ring, we can look at the function, those functions that are supported on this finitely many union of cones bounded above by some lambda i's. Okay. So, indeed we will be only interested in later, like if you study further representation theory, like for example BGG category and so on, that are associated with semi-simple algebras. So, we will be interested in representation, it could be infinite dimensional representation, those representation that actually has some kind of Jordan-Holder series with respect to Verma modules. Okay. So, you have like filtration whose successive quotients will be isomorphic to Verma modules. So, in particularly the character of those modules can be written as some finite sum of like Z combination of Verma modules, the character of Verma modules. So, in particularly the support of that will be contained in only union of this S of lambda i's. So, that generality only we will be actually working with. So, because otherwise the finiteness will be lost, we will not be able to actually multiply the character and so on. So, that motivates us to define the character ring as follows. Okay. So, we take the definition of character ring to be the following. So, here is the definition, the character ring. So, the all manipulation of the characters are done in this ring. So, what is this? By definition, you denote it by this curly R. Okay. This is the set of all functions from H star to Z, okay, or Z plus. So, that satisfies the following conditions. So, let us include actually Z in the codomain, okay, so that we can actually kind of include more functions, there is no issue. So, this is the set of all functions f from H star to Z, okay, such that if you look at the support of this f, okay, the support of f, so which is by definition those mu in H star such that f of mu is being non-zero. We are only interested in the support, and we demand that this is contained in union of S of lambda I for some lambda 1 etc. lambda k in H star. Note that S of lambda can be defined for any element of H star. Okay. So, such set we take it. So, you take all possible functions whose support is contained in finitely many cones or bounded above by this lambda 1 etc. lambda k. So, now it is easy to see that the character of V of lambda and the character of the Verma module both lie in this ring. Okay. And in particularly we can actually conclude that any finite sum will be there. Okay. Let us make a proportion. So, this proportion tells it is indeed a ring. So, we have to tell what will be the addition. The addition is obvious, addition will be the pointwise addition. So, given two function, okay, let us define it here. So, given f and g from R, then f plus g is defined to be from H star to Z. So, you take f plus g of mu is defined to be just f of mu plus g of mu for all mu in H star. So, this defines addition of these two characters. So, we are going to call any element of this ring to be the character. Okay. So, they are indeed virtual characters. So, they may not be actually character of some representations. We will see like how one can actually interpret all those things. So, now if we take f g from the ring, so we can also define the product being the convolution product, okay, the f g, which is again function from h star to z, f g of mu is defined to be. So, now you can consider f of mu g of mu, okay. So, it is not the pointwise product, because if you think about it, we want to use exponential notations to denote the character. So, there we want actually e power lambda times e power mu to be e power lambda plus mu. Because of that product, we actually get convolution product here. So, this is defined to be summation f of gamma 1 f of g of gamma 2. So, g of gamma 2, where gamma 1 plus gamma 2 is being mu. Okay. So, you take all possible gamma 1 gamma 2 from h star such that gamma 1 plus gamma 2 is equal to mu. So, this is the convolution product that you define on this ring. So, with respect to this, we want to claim that this R becomes actually ring. Okay. So, R is a ring. So, what we need to prove? We need to prove that the addition and multiplication is closed. Okay. So, because we have the constraint that support of f is indeed contained in finitely many cones, that should be true for the addition as well as the multiplication. So, it is indeed very easy exercise to see. So, I will just write down the relation. So, if you take f and g, if you look at f plus g, then the support of f plus g is easy to see that it is contained in support of f union support of g. Since support of f is contained in the finitely many cone and support of g also contained in the finitely many cone, that implies that support of f plus g is contained in finitely many cone. So, this implies f plus g is again inside R. So, if you begin with f g in R. So, now what is about the product? So, product is little bit tricky, it is not that hard actually. So, if you take support of f, let us say it is contained in union of s of lambda I range from 1 to k, and without loss of generality we can also assume that the number of s of lambda i's that appear in G also same. So, then you can just say that support of f is contained here, support of G is contained in union of s of mu j is j range from 1 to k again. So, we can actually just add the extra terms on the right side and then match that number of s of lambdas and s of mu's that appear, they are same. So, then it is easy to see that the support of f g, so because it is a convolution product, so this is going to be contained in the union of s of lambda I plus mu j, where I j runs over between 1 and k. Okay. So, since s of lambda i's are finite, s of mu j's are finite, so s of lambda I plus mu j's are finite. So, the product is indeed contained in this union, and this implies f g is again element of the ring. So, this makes our character, so the set of characters is a ring. So, now you can actually see that so all the computations about the characters can be done in this ring. So, here we make this exponential notation or the convention, okay, to denote the element of the ring, okay, because that is much more convenient to work with. So, it is the same data, but we will restore it in the different way. So, note that the character is a function from h star to z. So, we have to, for given mu, we have to record what is f mu. Okay. So, if we choose a basis of this R, so then we will be able to easily actually write down this f in terms of the basis. So, we will actually choose the z basis. Okay. So, what is the basis that we are interested in? So, we can take the characteristic function. So, given lambda in H star, we can define this e power lambda, which is a map from H star to Z, where e power lambda of mu is defined to be, so in single hand notation, this is just the canonical delta lambda mu. Whenever lambda equal to mu, it is 1, otherwise it is 0. So, this is how you define e power lambda. So, these are called characteristic functions. Characteristic functions, of course, depending upon this lambda. So, now if you just vary over this lambda, it is easy to see that this e power lambda, lambda from H star. So, this will form a z basis. So, this will form a z basis. Okay, I am actually not saying this correctly. So, we do not want z basis. So, it will form z basis only for the characters whose support is finite. Okay. So, it is not wrong, it is actually maybe like I will actually make the statement here. So, this is z basis for the group ring. Okay. So, this is z basis for this group algebra over z H star. So, what is this z H star? So, let us actually go slow and then recall what it is. So, so the ring R is nothing but set of all function from H star to z such that the support of f is contained in the finitely many cones. Union of S of lambda is I range from 1 to k for some lambda 1 etcetera lambda k from H star. So, this is our character ring. So, now we also have this important sub ring. So, let us take this as the definition. So, this is by definition you can take it to be those f in R such that the support of f is indeed finite. Okay. So, for example, if you start with finite dimensional representations, then the support of character of those finite dimensional representation will be finite. Okay, that is obvious. So, this is indeed isomorphic to the group algebra generated by H star over this z. Okay. So, now these characteristic functions obviously form a basis for this z basis, because when we say z basis, then we are only considering the finite sums. Okay. So, now how one can interpret general element f in R. So, general f in R can be reinterpreted as follows. So, you write in terms of these characteristic functions. So, we have to record all this f of mu. Okay. So, then f you can write it as summation f of mu e power mu, where mu runs over H star. So, this is the way you reinterpret f in terms of the characteristic function. Okay. So, this summation we want to think it as a formal sum, because most of the time this summation is going to be infinite. For example, if you consider Verma models, so this sum is infinite. Okay. So, we want to think this as a formal sum. So, there is actually very nice algebraic interpretation of these sums as a limit of something, but anyway you can take it to be formal sum and then you can work with this, not a problem. So, now it is clear that if I take in terms of this, if you write given two elements of R in terms of this characteristic functions, characteristic functions, then how the addition and the multiplication they are defined in terms of this exponentials. Okay, let us see what it is, how one can write it. So, given f and g in R, let us write f equal to summation c mu e power mu and then g to be summation d mu e power mu. So, then f plus g is nothing but summation c mu plus d mu e power mu. So, that is how f plus g is defined. So, what is about the product? The product is f into g is nothing but summation, again there will be another summation because this is a convolution product. So, you fix the e power mu here and then you take e power gamma 1, okay, sorry. So, you are going to multiply them and then you are going to collect the coefficient of e power mu. So, here the interior sum will be the summation c gamma 1 times d gamma 2, where gamma 1 plus gamma 2 will be mu, and this mu runs over all h star. Okay. So, this is how you interpret f plus g and f g. So, now if the supports are finite, there is again like very nice way of reinterpreting things. Okay. So, note that if the support of f is finite and if you write it as, okay, support of f to be some, let us say mu 1 etcetera mu r. So, then f is nothing but some c mu 1 e power mu 1 plus etcetera plus c mu r e power mu r. So, this is how we write. Okay. So, indeed when we actually work with the characters that comes from the finite dimensional representations, we will be able to actually cut down this h star to the weight lattice. Okay. So, we will be working with group ring generated by the weight lattice, okay, which is sitting inside eject h star. So, we will actually make the comment about it later when we consider the finite dimensional representations. Okay, I will stop here. So, we will continue with the character theory in the next class. So, ultimately we want to prove the character formula for the finite dimensional irreducible representation. So, which is given by Weil character formula, which gives some closed formula for the characters of finite dimensional irreducible representation. I will stop here, we will see in the next class.